Hello everyone, Chapter 6, Scatterplot, Association and Correlation. This is the main content of Chapter 6. We'll take you through the meaning of correlation, the meaning of associations, and why we need them, and how can we profit from them and benefit in order to take actions or decisions. Thank you. The main objective of this chapter and to learn from it is to look at how the scatterplot can be a very good description of the relationship or association between two variables. And then we're going to show you quantitatively how to calculate the correlation or the strengths between two variables given the relationship is linear. We will also, in the end, make a very clear distinction between correlation and causation. Scatter plots, it's as you can see in front of you, consist of two dimensions. That's why we call it the two-dimensional plot, where you have the horizontal line here and the vertical line is there. Usually the horizontal line is discussed or described as the independent variable, and the vertical axis is called the dependent variable. In many cases, this vertical, we give it a symbol like the letter Y, and the horizontal as independent, we call it X. So that means this is an X and Y plot where you have multiple points in this graph representing a relationship between the two variables X and Y. In many cases, this scatter plot in terms of points could give us a kind of idea in terms of visual inspections that there might be kind of association between the two variables, which is the case in front of us. So you can see on the horizontal line the title or the axis called oil price in US dollar, while the y-axis is the exchange rate between the Canadian and the US dollar. You can immediately get information from this graph by saying this graph suggests that there is positive or clear positive association or relationship between the two variables X and Y, which means when the oil price increases, this also associated with the increase in the exchange rate between the Canadian and the US dollars. So, and definitely because it's a positive, it also says another statement which confirms the positive relationship, which says if the oil price decreases as well as the exchange rate decrease. So since we have a positive relationship, both variables will go in the same direction, whether they go up together or go down together. So this is very important to see this. Next, it's will show you that there are multiple relationships, one of, in terms of polarity. So you need always to give a sign like positive or negative. It's very obvious, this top um, scatter plot. It's basically suggests that there is a downward direction, which means negative relationship, while the bottom graph it shows that there is a positive relationship. It's very critical as well is to make sure that in this chapter and in this course we are basically focus on a very important forms called linear relationship, which means the scatter plot that you have seen before can be fit in a line. If the dots on the scatter plot shows kind of curvature or not linear situation, this will not be the topic of this course. So basically we focus only on the linear relationship form, which is very, very important because every single thing we're going to discuss today will be basically based on the concept and the assumption that the relationship basically is linear. If it's non-linear, definitely there are other content, not in this course, but there are other content or outlines can discuss this nonlinearity and how to deal with nonlinearity. As I'm going to show you in the end of this session, that is really very important to discuss the linearity versus nonlinearity, and how can we, if we face data that shows kind of nonlinearity or curve, not linear, what should we do? So we're going to discuss that in the end of these slides. Another point which is really related to the relationships, not only the direction, negative or positive, also the strengths. Strengths, it means whether the relationship is strong or weak, or maybe no relationship at all. So how can we do that? Visually, if you see very clear trend going up or going down around, and the points are a little bit close to each other, then you immediately know that there is a strong relationship. When the points are scattered and going far from each other, then you know that the relationship is going to be weak. And if the scatter is really very big in terms of where you can't really find any pattern, then it's really very clear that this relationship is not anymore there. As usual, outliers is a concern of any data analyst and data scientist or anyone who deals with data. Outliers could really affect the whole analysis, whether you are studying one variable, which we call it univariate, or two variables, like in this chapter, we call them bivariate because we are analyzing two variables at the same time. While if you go back to chapter 4 and chapter 5, whether we studied qualitative or categorical data, as well in chapter 4 or in chapter 5, we studied the quantitative or numerical data. We basically analyzed each variable separately without making any connection. For that reason, chapter 4 analysis, chapter 5 analysis, we call it univariate analysis, while starting chapter 6, going through chapter 7, since we are going to analyze two variables at the same time, we call it bivariate for two. This is basically what I just mentioned here. This is what we call it bivariate analysis. Again, maybe this could be a part of what I said at the beginning, that we will always have two dimensions or two variables or two axes. One is called x, one is called y. The x is always representing the independent variables, and always we put it as horizontal line, while the y variable, which is the dependent variable, we always represent the vertical axis in the two-dimensional graph. It's very fundamental to understand that each variable x and y, they have scientific names like dependent and independent. If you look at the last bullet here, you find out that usually x is called independent and y we call it dependent. However, in many textbooks and even in workplace, sometimes instead of using independent and dependent, we use the words explanatory or predictors. Those are for the variables related to the independent. So because independent, they are trying to explain or to assess the value or the changes happening in the dependent variable. That's why the independent variable, which means x, sometimes we call them explanatory variables, and because we use them to predict the value of y, we call them predictor variables. Response variables or variable, in this case, we have represent in fact the dependent variable, which is the y, which is the vertical axis. Again, explanatory or predictor or independent, they are the same as x. Response variable, dependent variable, is the same as y. X will be put on horizontal line, while the y is on the vertical axis. Now, once we finish with the scatter plot, in Excel you can build a very simple scatter plot. If you have two columns, you can easily ask Excel to insert a scatter plot that is really easy to develop. And then you can also using built-in function inside Excel to calculate or to quantify this relationship. And this quantified relationship, we call it correlation coefficient. And usually we use the symbol small r here. You can see here in the equation, small r means the correlation coefficient between any two variables. Hopefully the relationship, as I mentioned, has to be linear. Hadn't the relationship linear, then we cannot use any of the equations that you see in front of you. Anyways, we have multiple ways to calculate this little r or small r or just correlation coefficient using the standardized form. And you can see here the equation refers to zx and zy, which is the z-score of x and z-score of y. If you, for each point in your data, so if you have a data set with 100 points, so for each point in the x-axis and column, you're going to calculate the z-score, and the same for the y. And then you take the multiplication between every pairs here, and once you get the multiplication for each point in your data set, then you take the summation, and this summation divided by n minus 1, n is the sample size, then you get what we call it correlation coefficient. Remember, in reality, you will not really use this equation because when you are working in a company, you will be using definitely software. One of them is maybe Excel. Excel has built-in function, and the built-in function use similar formula, either this one or the below one, because both of them, they're gonna give us the same result. The only difference between the top one and the bottom one is basically that the up one here using standardized data, which is really very important to understand why we do that. Sometimes if we have our data x and y are not having the same units, so maybe the y-axis is kind of dollars, but the x-axis may be volume or location or distance. Then in order to make the calculation easier or logical, you need to standardize the data using the z-score, as we discussed in chapter 5. So please go back to chapter 5 to know what is the z-score formula. It's very simple. But in many cases, sometimes we are interested to use the unstandardized form, which being represented by this equation here on the bottom. So you can see, maybe look at the right hand side here. You can see it's a little bit easier here to understand that all what we need to do is the deviation of x from its own average, the y also from its own average, and take the multiplication again, and take the summation. And after we get the summation of the multiplication, and this multiplication we call it product. Product means you multiply two or more terms to each other, and then after we get the summation of all products, then we divide by the standard deviation of x, the standard deviation of y. Once again, you can go back to chapter 5 to see the equation of standard deviation of x and standard deviation of y. N minus 1 again, n is the sample size. This right hand side form or term, it's the same as in the left hand side here, but it's a more simplified. So the next slide, we're gonna use this equation here. Remember this equation, we divide by sx, sy. So we need the deviation, and we divide by sx and sy. So I'm gonna get a very simple example here. Now, if we want to calculate the correlation between two variables here, we have x data here. So we can use, for instance, this data here. Imagine that we have, for simplicity, we're going to calculate the correlation between two variables, x and y. Each has 5 points. Of course, in reality, you might have 5 million points or 5,000. But just for simplicity, to see how the formula and the equation could be used in order to calculate the correlation. So now we have 5 points each. As you know from the previous slide, that we need the average of x and average of y. We need also the standard deviation of x and the standard deviation of y. So if you have this raw data, you need always to calculate the average and the standard deviation of each variable anyways. And then if you look at this little table on the right hand side here in the middle, you will find two columns here. One is called deviation in X, and the second one is deviation in Y. It's basically, if you look at the formula from the previous slide, we take each value from X, like the first one is 6 minus the average, which is here 14. So you apply this concept for every value in X. You do the same for every value in Y, taking into consideration that the Y variable has different average. Once you get that, we produce or develop the third column, which is the product, as I mentioned before, is basically the multiplication of the two columns here, each of two pairs here. So for each pair, so minus 8 as a result from deviation in X, first point, multiplied by minus 2 as a deviation from the first point in Y, then we get definitely 16. If you apply the same thing on each of the points that you have in a data set, if you have 100, you will do this 100 times, but in Excel you can really replicate it easily. So you do that and then you take the summation. So then you add up the products, 16 plus 16 plus 0 plus 5 plus 35, you're going to get 72. So now we've only calculated the top part, the numerator of the equation. We need to calculate the denominator now. So we need to divide the 72 by this value. The value is n minus 1, the standard deviation of X, standard deviation of Y multiplication. And as we know, we got this value up here. So the Sx is 6.2, the Sy is 3.9. You can see here we have 5 points, so n equals 5. So that means we need to subtract 1. So 5 minus 1 is 4. If we get this, we're going to come up with this value. If we divide 72 by 84.07, we get the number, and this number we call it correlation coefficient. It's very obvious. The relationship is not only positive, it's also very strong, because the value of correlation coefficient, as discussed before, it ranges from -1 to 1. That means if we approach 1 or -1, it means the relationship is strong or correlation is very strong. But when we are close to 0, the relationship will be weaker. If it's exactly 0, which it will not happen in reality, but if it's very close to 0, we can easily conclude that there is no relationship. When we go as far as we could from the 0, then the relationship will be stronger and stronger until it reaches a perfect correlation, which is not happening as well in reality, which is -1 and 1. It's not really happening, but just 0.8 is very close to 1, then it's a strong. Even if it was negative 0.856, it will also be considered as positive, as a strong, because the negative or positive doesn't matter. In the end, the absolute value is what matters. As long as the absolute value is close to 1, will be strong 1. Again, here maybe it's kind of a summary of what we just mentioned. We talk about that the correlation should be linear, and the data that we have is quantitative, because you remember from chapter 4, if you want to really find association between two qualitative, or what we call them categorical variables, we use contingency table, we call it crosstab, and usually we use Excel pivot table function in order to develop a crosstab, and this crosstab will give us a kind of idea if there is any association between two qualitative variables. Nevertheless, since in this chapter we are talking about correlation for quantitative data, the data have to be quantitative. If the data are qualitative, we cannot use these equations. You can only use the pivot table concept. Outliers are very important to make sure. If the outliers is an error, you have to remove it. If it's not, you have to keep it and to try to analyze the data with and without that. Again, this is just a summary of what I just mentioned, that the -1 and 1 meaning, and they have to be close to -1 and 1 to be considered as positive. Negative, it means reverse relationship between the two variables. It means if X increases, Y decreases. But positive, it means both of them, they go in the same direction. Finally, in this slide, you can see the last bullet is called correlation has no units, because it's a relative value. and the value, it could be any between -1 and 1. And if your data is using any units like a dollar or mix between dollars, as well as the other variable is in kilogram, or maybe distance in miles or kilometer, or any kind of units, it doesn't matter. In the end, correlation will be unitless or without unit. Yeah, this is again, correlation is sensitive to unusual observation, which means outliers. So in many cases, outliers could weaken the relationship between two variables. For that reason, we need always to discover whether we have outliers in our data. And probably you know that from chapter 5 again, I showed you using box plot, I showed you z-score, how we can use both of them to detect any outliers in our data. And if we have outliers, we need to deal with it in a scientific manner and not just removing them or adding them without any reason. This is a very interesting representation of correlation when you have not only two variables, but you have multiple variables. When I say multiple variables, I want you to envision your spreadsheet file, Excel file, that you might really have multiple columns, and you want to calculate the correlation between every two variables. The matrix or the table in front of you, we call it sometimes correlation matrix, or we call it correlation tables. It gives you the relationship between any two variables in your data set. So basically, it's very simple here. It looks like we have data about bookstore books. Like for each book, we have how many pages the book has, what's the width in maybe in centimeter, and what's the thickness in centimeter. And actually, this is not correct. The last column is called publication year, so this is in year. So this is a mistake here from the book, but I hope you understand this. So it's not double thick here, because if you look at the left hand side here, it's the same number of page width, it's the same thickness, is the same, but the last one has to be publication year. So this is again publication year. Anyways, any value in the middle here, it's a correlation coefficient between any two variables. So 0.003, which is really very close to 0, which we can easily say there is no correlation between number of pages of the book and the width of the book, which makes sense. But here, 0.813, it says that there is a really strong relationship between the number of pages and the thickness of the book, which makes sense. If the book has 1,000 pages, the thickness will be thicker than a book that has maybe 50 pages. So, and you can see every number here representing the relationship between any two variables. Sometimes it's very important to know whether you have relationship among different variables, because it facilitates how or in other words, to understand how your data is being analyzed, and then sometimes the data can tell us something important. Yeah, this is a very important part as well, probably the last or the fourth last part, which represent data, as you can see here, between two variables, irrespective of what they are. But if you look at the x-axis, called months since December 2008, but if you look at the horizontal vertical line, represent the price of solar systems in Germany. The price is in euro per watt in this case, so it doesn't matter now. But in the end, probably the researcher got the data between 2009 and 2013, and drew the plot, and the plot showed that there is really relationship, yes, but it's not linear. In this case, if it's not linear, because you can see very clearly there is a curve, so you cannot, it's like decaying, so you cannot really represent your data using the equation that we just used before. In this case, we need really to linearize it, and as you always know that in math we have a very interesting way to transform our data based on what we have. So in our case here, we use the log situation here, and you can see the log on the x-axis now. It's basically the log price. The previous one was only price, but when we took the log of the price and we drew it again, the curve or the data became more or less, it's better than just the curve. It became linear. In this case, we can calculate now the correlation using the equation that we use. That's a very important thing. Last part today in this slides, which is very clear, that's to differentiate between what we call it correlation and causation. So there is no way to conclude from high correlation that alone that one variable causes the other. You cannot really say that a variable can affect the other variable because of the correlation is high. We can only prove correlation through correlation coefficient, but causation variable cause the other variable to change is basically based on science or theories, or more what we call it face value or face validation, as we discussed in chapter 5. Again, there is or in the survey chapter, to be precise. So that means even if you have two variables are correlated and they don't really link to each other because that doesn't make any sense, then you have to know that there is a what we call it the third variable or lurking variable that affect both variables together. So it's very important to understand that every causation means correlation, but not every correlation means causation. That's very important. And by doing this, I end up my presentation, and hopefully you got something from that. I would suggest to go through it again if you didn't get every single thing, and take your time and have a nice study.